Let's talk about the electron double slit experiment. Before we do, let's refresh our memory about what happened when we did the double slit experiment with light. So we see that when the light hits the two slits, it creates two different wavefronts, and those wavefronts can interfere. Where the wave crests meet, the crest from the top wave and the bottom wave meet at the same place, or the trough from the top and the bottom wave, we end up with the wave being amplified. So the amplitude would be twice as big as one of the single wave fronts. On the other hand, where a wave crest meets a wave trough, they're going to cancel out, and so we end up with a black spot. And so we can see a series of stripes of dark and white based on whether the wave is interfering constructively or destructively. Now this raises the question, what happens if we were to do the same experiment, not with light, but with matter? So we can imagine doing this with a paintball gun, maybe a wall, and the wall has two doorways. So we're going to sit here and shoot at the wall, and of course if we hit the wall, the paint will just splatter here or here or here. But if we hit these open doorways, it's going to fly through and the paint's going to pile up, and we're going to end up with a door-shaped splatter of green paint on the opposite wall and a door shaped here. So we're in a room, we're shooting out of the room into, say, a hallway through these two open doors. And so we get these two places where if you're standing in the hallway here, you'll get hit with green paint in here. But of course, if you're hidden behind here, or if you're hidden behind these other walls, you're not going to get hit by paint. So pretty basic. Okay, let's predict the result when we do this with electrons. So we can imagine electrons, those are particles, just like little pellets of paint, and we've got these slits and some foil, and that's kind of like the doorways here. So we might expect that what we'd end up with, if we had something that maybe we have something that reacts with electrons when they hit and makes a little bright spot. I'll just use green here, but we'd end up with basically exactly the same result. So let's do the experiment. So I'm going to take you to a YouTube site. I'll just show you the site, and I'll link out, so if you can go to the original site and see about the original experiment. Okay, so we have electrons hitting a screen, and so they're going through the slits, and at first we don't see any pattern, but we're expecting, remember, that we'll see two stripes that correspond to the two slits. Okay, so there's still no pattern. Interesting. The electrons aren't behaving exactly as we expected. Remember, we wanted to have, or expected to have, two stripes that would be basically the same as the two slits. Still no pattern. I should point out that Dr. Tonomura sped up the experiment because it actually takes half an hour, so that's why there's jumps in the time. Now, if we look, we're starting to see a pattern emerge, but is it two slits? Is it two stripes? In fact, we can see it looks as if there's several stripes, in fact, many stripes. So if we look at the final image, we can see there's 1, 2, 3, 4, 5, and as we go further and further out away from where the slits were, the stripes get harder to see, but they're still there. So these are interference fringes. These are like the stripes we saw when we did the double slit experiment with light. So what's the one conclusion we have to draw? Since the multiple stripes we saw when we did the double slit experiment with light were a consequence of the wave nature of light, the only conclusion we can draw is that matter also behaves as a wave. Well, this is certainly not intuitive, but we can see there's this kind of interesting symmetry here. We saw that we thought that light was just a wave, and then we found out through various experiments that light also is made up of particles called photons. In other words, light has a wave-particle duality. It's got a dual nature. Well, we see that with matter too. Matter also has wave-particle duality, and this time the part that was intuitive was that matter is made up of particles, and the part that was really surprising was that matter behaves as a wave. If we do the right experiment, we can detect that wave nature. So by looking at the separation between those stripes, we can figure out the wavelength of the matter, and that's given by this equation. and you'll hear this pronounced a bunch of different ways. It's spelled de Broglie, but it's French, and so I believe it's de Broglie. Some people say de Broglie as if it's Italian, but I think it's de Broglie. Anyway, so here's the equation. This is the wavelength of the light. So we're going to put this into meters, and this is Planck's constant. So just to remind you, that's 6.626 times 10 to the negative 34th joule. Oop, I was going to say joules per second. That's a common mistake. 10 to the minus 34th joule seconds. And this is going to be mass. So the mass of the particle that we're talking about. And just put that in kilograms. So everything else will be in standard SI units. And this will be our speed of the particle. And once again, standard SI units, put that in meters per second. So I'll leave it as an exercise for you to see that if you take joules times seconds and divide by kilograms and meters per second, you'll end up with meters. So in class, we'll look at various examples of using this equation. For now, I just want to leave you with the conclusion that matter can behave as a wave.